Hi everyone, welcome back. In this video, we are going to cover top scenario-based microservices interview questions and answers designed specifically for experienced developers. If you are preparing for senior or mid-level backend roles, then this video will help you understand how to approach real-world problems in interviews. Because in experienced level interviews, you are not asked simple definitions. You are given real scenarios and expected to design solutions, handle failures, and justify your decisions. In this video, we will cover important scenarios like service communication, data consistency, distributed transactions, fault tolerance, scalability, and system design challenges. For each scenario, you will learn how to think step by step and explain your solution clearly and confidently. The goal of this video is to help you think like a senior developer and answer interview questions with practical insights. By the end of this video, you will be well prepared to handle real microservices interview questions. Let's get started. How do microservices communicate with each other? We'll explore the two main ways services talk, synchronous and asynchronous. Let's begin with synchronous communication. In this approach, one service makes a direct request to another and waits for a response. Most of the time, this is done using REST APIs over HTTP. Think of it like this. Service A picks up the phone and calls Service B. It asks for something and pauses until it gets an answer. This kind of communication is real time. Service A can't move forward until Service B finishes and responds. So when would this be useful? Let's imagine an e-commerce system. A customer clicks place order. That request hits the order service, but before it can confirm anything, it needs to talk to other services. First, it needs to check with the inventory service to see if the item is in stock. It sends a REST API call to inventory. Inventory processes it and replies. Maybe it says, yes, we have 5 units left. Only then can order service move to the next step. Payment. So it sends another synchronous call, this time to the payment service, asking to charge the customer's card. If that succeeds, the order service confirms the purchase. This whole process relies on each service being available and responsive in real time. If inventory is slow, everything slows down. If payment is down, the entire order fails. But it's also straightforward. You get immediate results. You can validate outcomes in one flow, and it's easy to trace because each call follows a single path. So when is synchronous the right choice? Use it when the service calling needs a decision or confirmation before continuing. It's great for things like processing payments, checking inventory, or getting user data. Basically any situation where the answer is required before moving forward. But keep in mind, this approach creates tight dependencies. If one service is unavailable or slow, the entire chain is affected. You need to design for timeouts, retees, and proper error handling. Now let's look at asynchronous communication. This method works differently. Instead of calling a service directly and waiting, the sender simply emits a message and continues on its way. The other service receives that message separately, on its own time. It's like dropping a letter in a mailbox. You send it and trust that the other person will pick it up and handle it later. Asynchronous communication usually happens through a message broker like Kafka, RabbitMQ, or AWS SNS. Now here's a practical use case. Let's say a user signs up for your platform. The front end calls the user service, which stores their information in the database. Now you want to send them a welcome email, but that doesn't need to happen right away. So instead of calling the email service directly, the user service publishes a message, user registered. The email service is subscribed to that event. It listens for the user registered message, and when it sees one, it sends the email. Maybe the analytics service is also listening. It logs the sign up data. Maybe a rewards service gives the user some bonus credits. None of these services talk to each other directly. They are all reacting independently to the same event. That's asynchronous messaging in action. So when should you go asynchronous? Use it when services don't need to respond right away, or when they shouldn't even know who's listening. It's ideal for background tasks, notifications, logging, or anything that doesn't block the main flow. This model keeps services loosely connected. If email service is down, the user can still sign up. The message will be picked up later when the service comes back online. Asynchronous communication makes your system more flexible and more resilient, but it also introduces more complexity. You will need to manage message queues, retrieves, and delivery guarantees. And debugging can be harder because events can be processed out of order. So, how do you decide between the two? If your service absolutely needs an answer before it can move forward, like a payment response or a validation check, go synchronous. That's where REST APIs shine. But if the service is just publishing something that others might care about, like user signed up or order completed, then messaging is a better fit. The truth is, most modern systems use both. REST for core business flows, messaging for events and background actions. It's not about choosing one over the other. It's about using the right tool for the right job. Next question. What are the core principles of microservices architecture and how does Spring Boot support them? Microservices architecture is based on building applications as a collection of small independent services. Each service is responsible for a specific business capability and can be developed, deployed, and scaled independently. The core principles include loose coupling, high cohesion, independent deployment, and decentralized data management. Services communicate with each other using lightweight mechanisms such as HTTP or messaging. Spring Boot supports microservices by reducing configuration overhead and enabling fast service development. Each microservice can be built as a standalone Spring Boot application with its own embedded server. Spring Boot encourages separation of concerns by clearly defining controllers, services, and data layers. This aligns well with microservices, where each service owns its logic and data. Configuration externalization allows the same service to run in multiple environments without code changes. Spring Boot also integrates easily with cloud and container platforms, which are commonly used with microservices. In interviews, experienced developers are expected to explain that microservices are not just about splitting code. They are about designing services that are independent, resilient, and aligned with business domains. Spring Boot acts as an enabler, not the architecture itself. Next question. How do Spring Boot microservices handle service discovery and why is it required? In a microservices architecture, services are dynamic. Instances are created, destroyed, or scaled frequently. Because of this, hard coding service addresses is not practical. Service discovery solves this problem by allowing services to find each other dynamically at runtime. Each service registers itself when it starts and removes itself when it stops. Other services query the registry to locate available instances. Spring Boot microservices rely on service discovery to enable loose coupling between services. A service does not need to know where another service is running, it only needs to know the service name. Service discovery also supports load balancing. When multiple instances of a service are available, requests can be distributed across them automatically. Without service discovery, microservices become tightly coupled and difficult to scale or maintain. Failures also become harder to handle. In interviews, experienced developers are expected to explain why service discovery is essential in distributed systems, how it enables scalability, and how it prevents configuration-related failures in real-world microservices deployments. Next question. How do you handle inter-service communication in Spring Boot microservices? Inter-service communication is a critical part of microservices architecture. Services need to exchange data to complete business operations. Spring Boot microservices typically communicate in two ways: synchronous and asynchronous. Synchronous communication is commonly done using HTTP-based APIs, where one service waits for a response from another. Asynchronous communication is used when services do not need an immediate response. Messages or events are sent, and services process them independently. This approach improves scalability and reduces tight coupling. In real systems, network failures and latency are unavoidable. Therefore, communication must include timeouts, retries, and fallback mechanisms. Without these, a slow or failing service can cause a chain reaction and bring down the system. Choosing the right communication style depends on business requirements. Overusing synchronous calls can reduce system resilience, while asynchronous communication adds complexity. In interviews, experienced developers are expected to explain communication patterns, trade-offs, and how failures are handled gracefully in Spring Boot microservices. Next question: how do Spring Boot microservices handle data management and database design? In microservices architecture, each service should own its data. Sharing a single database across multiple services creates tight coupling and defeats the purpose of microservices. Spring Boot microservices follow the principle of decentralized data management. Each service has its own database or schema, which allows independent evolution and deployment. This design improves scalability and fault isolation. If one service's database is slow or unavailable, other services are not directly affected. However, managing data across services introduces challenges. Transactions across multiple services are difficult. Instead of traditional distributed transactions, systems rely on eventual consistency. Data duplication is common in microservices. Services may store copies of data needed for their operations. This improves performance but requires careful synchronization. In interviews, experienced developers are expected to explain why database per service is important, how consistency is handled, and what trade-offs exist when designing data models for Spring Boot microservices. Next, how do you design microservices for fault tolerance and resilience in Spring Boot? Fault tolerance is critical in microservices because failures are inevitable in distributed systems. Services can fail due to network issues, high load, or infrastructure problems. Spring Boot microservices must be designed to handle these failures gracefully. A service should not crash or block indefinitely when another service is unavailable. Timeouts prevent services from waiting forever. Retries help recover from temporary failures. Circuit breakers stop repeated calls to a failing service and allow it time to recover. Bulkhead patterns isolate failures so that one slow component does not consume all system resources. Fallback mechanisms provide default responses when dependencies are unavailable. Monitoring and health checks are also part of resilience. Systems must detect failures early and respond automatically. In interviews, experienced developers are expected to explain that resilience is a design mindset. Spring Boot provides tools, but developers must design services assuming that failures will happen and plan accordingly. Next question: describe a common cascading failure scenario in microservices and how you debug it. A cascading failure happens when one failing microservice causes multiple dependent services to fail. For example, a downstream service becomes slow due to database issues. Upstream services continue sending requests and wait for responses. Their threads get blocked, thread pools become exhausted, and soon those services also start failing. From the outside, it may look like the entire system is down, even though the root cause is a single slow service. Debugging starts by checking system-wide symptoms. Response times increase, error rates spike, and thread pools show saturation. Logs often show timeout errors rather than clear failures. The next step is tracing requests across services. Traces usually reveal where delays are happening. Metrics help identify which service is consuming most time or resources. Once the root service is identified, the fix usually involves adding timeouts, limiting retries, and introducing circuit breakers. This prevents failures from spreading. In interviews, experienced developers are expected to explain not just what cascading failure is, but how they recognized it, isolated the root cause, and changed the system design to prevent it from happening again. This shows real production experience. Next, how do you debug high latency issues in Spring Boot microservices? High latency issues often appear gradually rather than as sudden failures. Users may report slow responses even though the system is technically up. CPU and memory may look normal, making the issue harder to diagnose. Debugging starts with identifying where time is being spent. Metrics help determine whether latency comes from the application, database, or external service calls. Distributed tracing is critical here. It shows how long each service and each operation takes during a request. Often, one slow database query or external API call dominates the response time. Logs are used to correlate slow requests with specific inputs or conditions. Sometimes, latency only happens for certain data sizes or edge cases. Common fixes include optimizing queries, adding caching, reducing payload size, and tuning thread pools. Sometimes the fix is architectural, such as switching synchronous calls to asynchronous processing. In interviews, experienced developers should explain how they move from symptoms to root cause and why guessing without data usually makes latency problems worse. Next question. Explain a production issue caused by misconfiguration and how you troubleshoot it. Misconfiguration is one of the most common causes of production incidents in microservices. A typical example is incorrect timeout, connection pool size, or memory configuration. The application may work fine in lower environments but fail under real production load. Symptoms can include frequent timeouts, connection errors, or unexpected restarts. Logs may show errors, but the real issue is configuration, not code. Debugging starts by reviewing recent changes. If code has not changed, configuration becomes the prime suspect. Comparing production configuration with staging or previous working versions often reveals the issue. Metrics help confirm whether resources are being exhausted. For example, connection pool metrics may show all connections in use, indicating misconfigured pool size. The fix usually involves correcting configuration values and redeploying or reloading configurations safely. Long-term fixes include validation, sensible defaults, and better environment parity. In interviews, this question tests whether candidates understand that many failures are operational, not coding mistakes, and how careful configuration management prevents outages. Next question. How do you debug memory leaks in Spring Boot microservices? Memory leaks are dangerous because they often appear slowly and worsen over time. A service may run fine initially, but gradually consume more memory until it crashes or becomes unresponsive. Restarting the service temporarily fixes the issue, but the problem returns. Debugging starts by observing memory metrics. A continuously increasing memory usage without release is a strong indicator of a leak. Garbage collection logs often show increased frequency without effective cleanup. Next, heap analysis is used to identify objects that are retained unexpectedly. Common causes include unbounded caches, static references, and listeners that are never removed. In microservices, memory leaks can also occur due to excessive object creation from high traffic or improper handling of large responses. Fixes include limiting cache size, cleaning up resources properly, and reviewing object lifecycle management. In interviews, experienced developers should explain that memory leaks are rarely obvious and require systematic observation, not trial and error fixes. Next, describe how you debug a production issue that you cannot reproduce locally. Some production issues cannot be reproduced in development environments due to scale, traffic patterns, or real user behavior. In such cases, debugging relies on observation rather than reproduction. Logs, metrics, and traces become the primary tools. The first step is narrowing down the conditions under which the issue occurs. This may involve identifying specific users, requests, or times when failures happen. Next, additional logging or diagnostics may be enabled temporarily but carefully to avoid performance impact. Feature flags are often used to isolate suspected code paths. If necessary, a controlled fix or workaround is applied to reduce impact while deeper analysis continues. The goal is to stabilize the system first, then fully understand the root cause. In interviews, experienced developers are expected to explain a calm, structured approach to debugging under uncertainty. This demonstrates maturity, responsibility, and real-world problem-solving skills. Next question. Describe a real-world authentication failure in microservices and how you debug it. Authentication failures in microservices often happen due to misaligned security configuration between services. A common scenario is when one service successfully authenticates a request but downstream services reject it. From the client's perspective, the request suddenly fails even though login was successful. Debugging starts by identifying where authentication breaks. Logs usually show unauthorized or forbidden errors in downstream services. Tracing helps confirm whether authentication information is being forwarded correctly. In many cases, the issue is missing or invalid credentials in inter-service communication. The upstream service may authenticate the user, but the downstream service does not recognize the authentication context. Another frequent cause is token expiration or clock skew between services. Tokens may appear valid in one service but expired in another. The fix usually involves ensuring consistent authentication mechanisms across services and validating token handling in every hop. Centralized authentication logic reduces such issues. In interviews, experienced developers are expected to explain how authentication failures propagate in distributed systems, how they identify the exact failure point, and how they design systems to avoid inconsistent security behavior across microservices. Next, explain a security incident caused by misconfigured authorization rules. Authorization failures are more dangerous than authentication failures because they can expose sensitive data. A common incident occurs when access rules are too permissive. For example, an API endpoint intended for administrators is accidentally accessible to regular users. This often happens due to incorrect role checks or missing authorization rules. Such incidents are usually detected through audits, logs, or unexpected user behavior rather than immediate system failure. Once discovered, the first step is to restrict access immediately to prevent further exposure. Debugging involves reviewing authorization logic and mapping roles or permissions to endpoints. Logs help identify which users accessed restricted resources. The fix often requires tightening authorization rules and adding automated tests to verify access control. Clear separation between authentication and authorization logic helps prevent similar mistakes. In interviews, experienced developers should explain that authorization errors are often silent but high risk. Interviewers want to hear how you prevent overexposure, validate access rules, and design secure APIs that follow the principle of least privilege. Next question. How do you handle and recover from a leaked secret or credential in production? Leaked secrets are critical security incidents that require immediate action. A leak can happen through logs, source code repositories, or misconfigured environments, Once detected, the first priority is containment. The compromised secret must be revoked immediately. Next, new credentials are generated and deployed securely. Systems using the old secret must be updated quickly to restore functionality. Logs and access records are reviewed to understand how the secret was exposed and whether it was misused. This helps assess impact and prevent further damage. Long-term fixes include removing secrets from code, improving access controls, and enforcing regular secret rotation. Monitoring is also strengthened to detect similar issues early. In interviews, experienced developers are expected to explain both the technical response and the process response. Interviewers look for calm, structured handling of incidents, not panic-driven fixes. This demonstrates real-world security maturity. Next question. Describe a common security vulnerability in REST API and how you prevent it. One common REST API vulnerability is insufficient input validation. If API accepts user input without validation, attackers can exploit this to access unauthorized data or overload the system. Another frequent issue is exposing too much information in error responses. Prevention starts with validating all incoming requests. API should reject invalid or unexpected input before reaching business logic. Error responses should be clear but not reveal internal system details. Authentication and authorization must be applied consistently across all endpoints. Missing protection on even one endpoint can compromise the entire service. Rate limiting is also important. Without it, attackers can overwhelm API with requests, causing denial of service. In interviews, experienced developers are expected to explain that API security is not a single feature. It is a combination of validation, access control, safe error handling, and defensive design. This shows understanding beyond basic security concepts. Next question. How do you investigate a suspected security breach in a microservices system? Investigating a security breach starts with evidence collection. Logs, metrics, and audit trails are reviewed to identify unusual access patterns or behavior. Traces help determine which services were involved and how requests moved through the system. The next step is isolating affected services to prevent further damage. Access may be temporarily restricted while investigation continues. Once the attack vector is identified, the vulnerability is fixed. This may involve changing configuration, patching code, or strengthening security controls. After recovery, a post-incident review is critical. The team analyzes what went wrong, what signals were missed, and how detection can be improved. In interviews, experienced developers are expected to explain a structured incident response approach. Interviewers want to see responsibility, communication, and learning from incidents, not just technical fixes. This reflects true production-level security experience. Next question. Explain the API gateway pattern and why it is important in microservices. The API gateway pattern is used as a single entry point for all client requests in a microservices system. Instead of clients calling multiple microservices directly, all requests go through the API gateway. The gateway then routes requests to the appropriate backend services. This simplifies client-side logic and hides internal service structure. The API gateway handles common concerns such as authentication, authorization, rate limiting, logging, and request validation. This prevents duplication of these responsibilities across multiple services. Another important role of the gateway is request aggregation. Sometimes a client needs data from multiple services. The gateway can combine responses and return a single result, reducing network calls. Without an API gateway, clients become tightly coupled to internal services. Any service change can break clients. The gateway provides a stable contract and protects internal services from direct exposure. In interviews, experienced developers are expected to explain that the API gateway is not just a router. It is a boundary that improves security, scalability, and maintainability in microservices systems. Poorly designed gateways can become bottlenecks, so they must be lightweight and carefully designed. Next, what is the circuit breaker pattern and how does it prevent system failure? The circuit breaker pattern is used to prevent repeated calls to a failing service. In microservices, service failures are inevitable. If one service becomes slow or unavailable, continuously calling it wastes resources and spreads failure across the system. A circuit breaker monitors service calls. When failures exceed a threshold, the circuit breaker opens and blocks further calls to the failing service. Instead of waiting for timeouts, requests fail fast. After a cooldown period, the circuit breaker allows a few test requests. If the service recovers, normal traffic resumes. If not, the circuit remains open. This pattern protects thread pools, prevents cascading failures, and improves overall system stability. It also allows dependent services to continue functioning, often using fallback responses. In interviews, experienced developers are expected to explain real failure scenarios where circuit breakers saved the system. Interviewers want to hear why failing fast is better than waiting and how circuit breakers change system behavior under stress. Next, explain the Saga pattern and how it handles distributed transactions. The Saga pattern is used to manage distributed transactions in microservices. In microservices, each service has its own database. Traditional database transactions cannot span multiple services without tight coupling. The Saga pattern solves this by breaking a transaction into multiple local transactions. Each service performs its operation and publishes an event when it completes. Other services react to that event and perform their own operations. If one step fails, compensating actions are executed to undo previous successful steps. This ensures data consistency over time rather than immediately. The Saga pattern supports eventual consistency and avoids locking resources across services. However, it requires careful design. Services must be idempotent and compensations must be reliable. In interviews, experienced developers are expected to explain why traditional transactions do not work in microservices, how sagas reduce coupling, and what complexity they introduce. Interviewers often look for real examples, such as order processing or payment workflows. Next question: what is the database per service pattern and why is it critical? The database per service pattern means each microservice owns its own database. No other service is allowed to access that database directly. This ensures strong service boundaries and independent evolution. If multiple services share a database, they become tightly coupled. Schema changes in one service can break others. Deployment becomes risky and slow. With database per service, each service can choose its own data model and scale independently. Failures are isolated. A database issue in one service does not directly impact others. The trade-off is data duplication and eventual consistency. Services may need to store copies of data owned by other services. This increases complexity but improves scalability and resilience. In interviews, experienced developers are expected to explain that this pattern is foundational for microservices. Interviewers want to hear why database sharing breaks microservices and how data ownership improves long-term system maintainability. Next question: explain the event-driven architecture pattern in microservices. Event-driven architecture is a pattern where services communicate by publishing and consuming events instead of calling each other directly. When something important happens, a service emits an event. Other services react to that event asynchronously. This removes direct dependencies between services. This pattern improves scalability and resilience. Services do not wait for responses and are not affected if consumers are temporarily unavailable. Events can be processed when resources are available. Event-driven systems are ideal for workflows, notifications, analytics, and integrations. However, debugging becomes harder because execution is distributed and asynchronous. Observability, idempotency, and proper error handling are critical. Without them, event systems can become unreliable and difficult to maintain. In interviews, experienced developers are expected to explain when to use events instead of synchronous calls, what problems event-driven architecture solves, and what new challenges it introduces. This shows architectural maturity.